Thank you for joining us for the workshop presenting the top 3 abstracts of Airways, Physiology, and Pathophysiology. We have some great talks lined up for you today, and we're very excited that you could join us. So just as housekeeping, if you have any questions, feel free to throw them in the chat or the Q&A, and we'll ask the speakers the questions at the end of their presentation. So without any further ado, I'll introduce our first speaker, Jacelyn Peabody-Lever from the University of Alabama at Birmingham, and take it away.
Thanks so much for that introduction. I'm thrilled to be able to share our project with you. I'm a 6th year in the MD PhD program at UAB. I'm working in the lab of Dr. Stephen Rowe, and today I'll be sharing our project on how ivacaftor improves mucociliary clearance in vivo in diseased G551D transgenic ferrets. I have no relevant disclosures for this presentation. So as we're aware, cystic fibrosis is a disease characterized by delayed mucociliary clearance. In this cute cartoon schematic, we can see a healthy mucociliary escalator on the left, where when it's functioning well, impacted particles in the mucus are pushed up and out of the lungs via the mucociliary escalator, where they can either be swallowed or coughed out. In diseases like cystic fibrosis, where you have pathologic mucus, there is delayed clearance and it just does not function well because you have an unhealthy mucociliary escalator. Ivacaftor is a potentiator therapy which works by increasing the open probability of CFTR, and it accelerates mucociliary transport in vitro and MCC in patients. However, there's a gap in knowledge where we don't actually understand how MCC abnormalities and ivacaftor response relate to pulmonary disease. So the objectives of this study were twofold. First, to characterize in vivo MCC in G551D knock-in transgenic ferrets and compare that to wild type, and also assess how clinical disease and MCC evolve with cessation of ivacaftor therapy. We also sought to investigate the relationship between diseased areas by micro-CT with regional MCC. This is a schematic of our experimental design. These are G551D knock-in ferrets that were treated in utero with ivacaftor from about the time analogous to 3rd trimester in pregnancy in humans, and treated postnatally through their adult life. We received 6 ferrets from the University of Iowa that were transferred to UAB. At the time of transfer, we did do repeat baseline measurements with them on ivacaftor, with our 2 outcomes being micro-CT and MCC. Then ivacaftor was withdrawn for 1 to 3 months before we repeated MCC and micro-CT. And we had wild-type ivacaftor naive ferrets to serve as controls and an N of 8 for those. So we had 6 G551D ferrets and 8 wild-type ferrets. To start, I want to show you how the CF ferrets get progressive disease off of ivacaftor. The video on the left here is one of the ferrets when they first arrived. You can see she's virtually indistinguishable from a control ferret. She's interested in food, not showing any signs of lethargy. On the right here, we have a video of an ivacaftor withdrawn ferret. He's been off of ivacaftor for 1 month. And what you can appreciate here is he's tachypnic, he's skin and bones, looks lethargic, showing no interest in the food, and overall just looks like a sick ferret. This is what one of the scans looks like in a G551D ferret withdrawn from ivacaftor. We see these ground glass opacities by micro-CT, as well as some muco-obstructive lesions. And then grossly, we also see abnormalities, where in this right lower lobe, you see that it's red and inflamed, demonstrating hepatization in the lungs. We also have these subpleural muco-obstructive abscesses that are present in our CF ferrets. And this is really emblematic of what we saw in all of the animals withdrawn from CF. So of the 6 ferrets we received, 1 had to be palliatively euthanized. He demonstrated spontaneous GI bleeding. We also had 1 die spontaneously of what we think was respiratory failure. All of the ferrets withdrawn from all of the G551D ferrets withdrawn from ivacaftor demonstrated low pulse ox saturations between 89 and 93%, whereas when they arrived, they were between 96 and 98%, and wild-type ferrets are 99 to 100%. So they did show clinical symptoms of disease, and then we had substantial weight loss in the withdrawal group, about 15%. Originally, we planned on withdrawing these ferrets for 3 months, But due to COVID-19, we did have to end the study early after only 1 month of withdrawal due to COVID-19. So our first endpoint measurement was in vivo micro CT scans to evaluate lung disease. And what we do here is we do respiratory gating, which ensures that we capture the images when the lungs are fully inspired. And this is just to show you what a control ferret looks like using our imaging modality. And then our second outcome measure was a whole lung mucociliary clearance assay, or MCC assay. And what we do is we intubate the ferrets with uncuffed tracheal tubes. We nebulize about 25 millicurie of technetium-99 in 2 milliliters of saline over 10 minutes. And we do dynamic SPECT-CT imaging over the course of an hour. So here is, a sped up video of what that looks like over time. So it starts very red hot radioactive and fades over the course of an hour. And you can see that radioactivity is being pushed up along that mucociliary escalator. And then from that dynamic data, we can get this heat map and quantify percent clearance per minute, which is denoted in this heat map. We correct for radiation decay, and we also correct for muscle absorption. And this is a very powerful in vivo mucociliary clearance assay, which allows us to calculate whole lung clearance over time. And we also use a linear mixed effect model, which allows us to control for repeated MCC studies to assess the rates of change and control for central peripheral deposition. And we do repeated measures and this mixed effects model to incorporate multiple technical replicates while treating each animal as an independent variable, which allows us to improve the precision of the point estimate given the limited N of these G551D ferrets. So this is a summary of our MCC data. What we found was that MCC in the ivacaftor treated group was significantly faster than the withdrawal group. These are representative heat maps here, where we see very warm colors representing fast clearance in the ivacaftor group, compared to cool colors representing slow clearance in the withdrawn group. That's denoted dynamically here with technetium particle retention over time. The more particles retained, the less that were cleared. So in red, we see the off ivacaftor group compared to the on ivacaftor group. And when we look at a snapshot at 60 minutes at the end of our dynamic SPECT study, we actually see a 6.4% increased clearance in the ivacaftor group compared to the withdrawal group using that mixed effects model I alluded to previously. So this was really exciting for us that we see in vivo ivacaftor improves mucociliary clearance. Then our second outcome measurement was looking at micro CT scans. So up top is a representative control coronal section. And what we see here is that the lungs are black and air-filled. So the quantitative unit used in CT is called a Hounsfield unit, and it's arbitrarily assigned densities. So air is assigned a density of -1,000, bone is assigned a density of +1,000, and water is 0. So lung parenchyma that's healthy, that should be air-filled, is very negative Hounsfield units. And things that are soft tissue or any kind of consolidation on the lungs has more positive Hounsfield units. So a very healthy lung scan looks like this, pretty uniformly black. And this is a 3D volume rendering of the micro CT within the lung mask from this data here. And then below, I have a representative G551D ferret that was off of ivacaftor. And what we can see here in the 3D volume rendering is that this apical lobe is almost completely opacified. And we see a lot more heterogeneity throughout the lung where it's not just all blue and air-filled. We have some areas that show this ground glass opacity and this muco-obstructive type lesions. And then this was really a foundational observation which prompted us to look at co-localization between micro CT and MCC. Was I noticed that in this example here, in the area that was almost completely occluded and opacified by micro CT, was also the area that did not show good clearance by MCC. So that prompted us to ask, is there a relationship between MCC rate and these micro CT lesions? So we did that study. So using our 8 wild type control ferrets, we have the MCC technetium particle retention on the left. And on the x-axis, we have the CT radiodensity Hounsfield units on the right. And we see the significant negative relationship where in areas that show any kind of opacification, there is decreased clearance, and in areas that have that are not opacified, that are healthy black parenchyma, actually have the fastest clearance. So then we looked at that by treatment group. So in our CF withdrawal group, we also have a significant negative relationship here, where in areas that are opacified, we have the slowest clearance. So this is representing opacified areas, and this is slow clearance versus areas of, when we look at the G551D animals that are on ivacaftor, we actually see an opposite relationship compared to what we saw in the CF withdrawal group or the wild type. And then again, here is the wild type control on top. So with ivacaftor treatment, MCC was fastest in regions with greater opacification by micro-CT. That was very surprising to us and an interesting observation, and raises the question of, does CFTR potentiator therapy stimulate clearance as a physiologic response to mucus load and infection? And this is kind of goes along thinking about patients who are treated with highly effective modulator therapies that experience a purge. So they're given Trikafta or ivacaftor, and the first week or so of treatment, they experience significant increase in sputum production or coughing up all of this junk after they're receiving this therapy. Is that what we're seeing in these ferrets? And our lab also has data looking at autoregulatory mechanisms of mucus clearance. So are we normalizing the mucus so that it's actually the mucociliary escalator is then able to respond to mucus load? So these are ongoing studies where we're trying to understand this opposite relationship that we observe between the CF on ivacaftor and the CF withdrawal groups. How are we actually getting faster clearance in regions with greater opacification by micro-CT? So in conclusion, ivacaftor withdrawal does induce CF lung disease in G551D knock-in ferrets. Ivacaftor does accelerate MCC in G551D ferrets, and it's similar to the wild type controls. And with ivacaftor treatment, MCC is fastest in regions with greater opacification by micro-CT, unlike those that are off of ivacaftor, which suggests that CFTR potentiator therapy may stimulate clearance as a physiologic response to mucus load. And we are doing further cohorts to validate these findings and increase our N. Again, this is a very exciting pilot study with an N of 6 G551D ferrets and 8 wild type controls. So lots more work to do here, but very exciting preliminary studies. And with that, I'd love to take any questions that the audience may have and acknowledge the UAB team, our collaborators at the University of Iowa, our core facilities at UABs, and our funding sources.
Thank you, Jacelyn. That was a very great talk. So we have some questions from the audience. The first question is, you describe a 6.4% improvement in mucus clearance with ivacaftor versus off ivacaftor. What is the difference in MCC in people with CF and G551D mutation who start ivacaftor? Is it similar?
So that is something that I should know offhand, and I don't. That work has been published previously, and I believe that the order of magnitude is actually greater in G551D patients than what we're seeing in these animals. But I will have to check back on the literature to know definitively. Can I phone my PI?
All right, so the next question is, I wonder if you tried to measure whole lung MCC, both wild type and G551D ferrets in a stimulated condition, for example, with acetylcholine treatment.
We have not done that. We do ex vivo imaging on the tracheas of these animals at the time of sacrifice. So what that entails, we use micro-optical coherence tomography, and instead of it being a whole lung mucociliary clearance measurement, we actually are able to look at small points along the trachea and the bronchi. And with that, we're able to measure mucociliary transport rates. So we do a stimulated, we'll stimulate with carbachol. and that increases cilia beat frequency and mucus secretion, both in our wild type controls and the G551D ferrets. But we have not done it in vivo, but that's a very interesting idea to consider for the future.
And then the next question is, how much is the variability observed in MCC post-ivacaftor treatment? This is actually a multi-part question. Also, have you tried the triple to see if you have higher efficacy? And did the ferrets have enough time to develop bronchiectasis or other clear structural damage?
So we have not tried Trikafta. We are still waiting on the pathology to come back from the sections of these animals. So to be determined, we do see some tree and bud lesions by micro-CT in a handful of the ferrets at baseline upon arrival, but it definitely got worse over time in those that had been withdrawn, especially for the one ferret that we got all the way out to 3 months post-withdrawal. He had the most severe disease. Can you remind me what the first part of the question was?
How much is the variability observed in MCC post-ivacaftor treatment between ferrets?
So within animals, it's very reproducible, but comparing the biological replicates compared to the technical replicates, we do see quite a bit of variability where some of the ferrets do have slower MCCs consistently than other ferrets. So we might have, there's quite a bit of biological variability. So we have about a 6% benefit on and off ivacaftor when we average the groups. But when we look at kind of our outliers, we had one ferret that had only about a 4% benefit on ivacaftor compared to off, whereas one of our responders actually had about a 15% difference on and off. So there is a range and some biological variability present on and off. But in terms of our repeated measures, when we do the baseline measurements, it's within 1% difference. And when we do the off ivacaftor measurements, it was also within plus or minus 1.5% or so. So it is reproducible, just there is biological variability.
That's great. Thank you very much. So I'm afraid we're out of time for more questions for Jacelyn. We've published some of them in the chat, so or rather in the Q&A. So if Jacelyn has time, possibly she could check the chat and help answer some of these questions. In the meantime, I think we'll introduce our second speaker. This will be Nan He from the University of Iowa.
Hello. Yeah. Good afternoon. Welcome to my presentation. My name is Nan He. I come from University of Iowa, joining Heart Lab. And the title of my presentation is Lung Function Studies in MUC5AC and MUC5B knockout ferrets. I do not have any disclosures. Mucus is an important barrier of respiratory surfaces. MUC5AC and MUC5B are the principal molecules in airway mucus. Study shows MUC5B expression affects inflammation and macrophage-mediated responses in the lung. However, the relationships between MUC5AC, MUC5B, and airway obstruction are still unknown. Our study will focus on the evaluation of pulmonary function on MUC5AC knockout and MUC5B knockout ferrets to figure out if MUC5AC and MUC5B are required to maintain lung function and how it works. Ferret is a good model to study physiology of a respiratory system. Firstly, the submucosal glands in mice and rats are only located in the proximal trachea, while ferrets have submucosal glands throughout their cartilaginous airways like humans. What's more, the predominant secretory cell type in cartilaginous airways of mice are club cells. In fairies and humans, the secretory cell is the goblet cell. In our ferret is the gold standard model of influenza and may help model early viral infections in lung disease. We have three hypotheses. The first one, MEC5B knockout and MEC5AC knockout fairies will have alerted pulmonary function. The second one, MEC5B knockout and MEC5AC knockout fairies will have poor mucociliary clearance. And the last one, MEC5B and MEC5AC are required for airway defense. This image shows how we generate the knockout fairies. We use CRISPR-Cas9 to generate MEC5B knockout and MEC5AC ferret models. Totally, we injected 3 GARDN-A into zygotes, and the GARDN-A were targeted in promoter, exon 1, and intron 1, respectively. Here you can see there are 3 deletions, and these 3 deletions are the primary mutations we used in my study. They are a short deletion in MEC5B exon 1, a large deletion from promoter to exon 1 of MEC5B, and a large deletion from promoter to intron 1 of MEC5AC. We quantified the proteomics in bio and mRNA expression in cells. For the proteomics, you can see for the MEC5B knockout ferrets, there's no MEC5B protein, and for the MEC5AC knockout ferrets, there is no MEC5AC protein. And then is the qPCR data. The qPCR data shows there's although there is a small MEC5B mRNA expression in the MEC5B knockout ferrets, but it's very lower than the control. And in the MEC5AC knockout ferrets, there's no MEC5AC mRNA expression. After confirming, we got 2 knockout ferrets. We evaluated the lung function in our models. We used the most new version of FlexiVent system to perform pulmonary function test. Here is a schematic image, and it tells how we set up the machine. Actually, we can get some parameters from FlexiVent system, and the 3 most important ones are inspiratory capacity, compliance, and the ratio of FUV divided FVC. The ratio of FUV divided FVC is an important clinical index to measure if a person has obstructive physiology. And we choose some Y-type ferrets, and we got the relative data from the FlexiVent system. We can see at 0.4 seconds, the ratio of FUV divided FVC is about 70%, the same as FEV1 divided FVC in humans. So we choose 0.4 seconds as the measurement time point. Now we will see the data one by one. The first one is the inspiratory capacity, the IC. In the MEC5B knockout group, we can see the IC increased significantly than the controls. And in MEC5AC knockout group, the IC decreased significantly than the controls. And for the compliance, I don't see there's bigger difference between the MEC5B knockout ferrets and the control ferrets, but the compliance from the MEC5AC knockout ferrets decreases significantly than the controls. And then is the ratio data. We can see in MEC5B knockout group, the ratio of FEV 0.4 divided FVC decreases over time, but in MEC5AC knockout, the ratio is opposite. The ratio increases over time. So all the three parameters tell us both MAC5B and MAC5AC are required to maintain lung function, but they play different role. Here is a short conclusion. MUC5B and MUC5AC are required to maintain lung health. MUC5B deletion results in airflow obstruction as Fibrosis age. Lack of MUC5AC leads to reduced compliance and lung volume. We also get the CFU data from the BAO. Firstly, for the MUC5B knockout group, we can say the CFU from the MUC5B knockout Fibrosis is significantly higher than the controls. But for the MUC5AC knockout, although the CFU is higher than the control, but it is not significantly. So the CFU data tells MUC5B is required to maintain lung defense in the ferret. Let's say if these two genes are related to MCC. From the images, we can see the beast on the control trachea moves a lot and fast during the 15 minutes, but on the MBC5 knockout trachea, the beats don't move a lot during the 15 minutes. And the speed data shows the MCC is lower than the control significantly. MCC5B knockout Fibrosis exhibits lower MCC compared to its matched wild type controls, and then in the hypothesis, the aberrant function comes from the alerted mucin structure on the airway surface. Then is the conclusions. First one, MAC5AC and MAC5B are required to maintain pulmonary function in the ferret lung. Second one, MAC5B is required for mucociliary clearance of small particles and may lead to airflow obstruction as animals age. The last one, loss of MAC5AC leads to reduced pulmonary compliance. And at last, I will thank everybody. Thanks everyone in my lab, John in her lab, and thanks everyone who attended the meeting. Yeah, that's all.
Thank you. That was a great presentation. We have a couple of questions that have come in from the audience. The first question is, what age were the ferrets when these studies were performed, specifically for the BAL microbiology?
Actually, when the ferrets are older than 3 months, we can perform the pulmonary function and we can get the BAL. So the data, most of the data are from adult ferrets.
And the next question is, what do you think the relationship is between MUC5B and airway colonization?
Thanks for the question. It's a good one. Because as the study shows, MAC5B is related to the infection of the trachea. So I think the MAC5B plays an important role to reduce the inflammation and other, yeah.
All right, and did either of the muck knockouts influence the ferret's ability to survive?
Yes, the actually, although I don't show the data today, but the MAC5B knockout reduce the rate of the ferret survive. Actually, I remember that the ratio of the knockout group is about 10%. And available of double knockout ferrets. Actually, we have double knockout ferrets now. We injected the Garner-A for the MAC5B and MAC5AC in the zygote, and we got some double knockout ferrets. But we still don't get the double homozygous knockout ferrets. So I don't show the data.
I see. Thank you.
Mhm.
And then the next question is that these are fantastic models. Do you see any remodeling of the secretory cells in the epithelia?
It's a good question. I'm doing some experiment on the ALR culture. I couldn't make a conclusion now, but yes, we are doing that. Maybe we will find something. Thanks.
And then I have one last question before we close. Is there a difference in the type of bacteria that you're culturing from the MUC5B knockout versus the MUC5AC knockout?
Could you repeat it one more time? Sorry.
Is there a difference in the types of bacteria that are being cultured from each model?
Oh, okay. I don't say there's a difference between the bacteria on the bowel.
All right, and I think we have one last question. Can you describe how you've quantified the mucin in the lung?
You mean the proteomics or the mRNA?
Either, yes.
Yeah. For the proteomics, we use the LS MCLS LS method to quantify the mucin protein in the bowel. And for the qPCR, we got the mRNA from the cells and then use quantify.
Okay, thank you very much. Oh, I think we have one last question. Have you tried to challenge these ferrets with bacteria?
We still don't challenge the ferries, but we may give a challenge on the ferries. In my lab, because we challenge some bacteria on other models, but still don't on the MEC5B and AC knockout ferries. But maybe we will try in the future.
Okay, thank you very much for a great talk, and thank you for the answers to those questions.
Mm-hmm.
And with that, I will introduce our final speaker, Annalisa Adante from the German Center for Lung Research in Berlin.
Hello, everyone. Thank you very much, actually, to give me the opportunity to present my work today in this workshop. So my name is Annalisa Dante, and I'm working in the laboratory of Professor Markus Mahl at Charité University Medical Center in Berlin. And it's a pleasure for me to give an overview about my project, preclinical evaluation of the novel mucolytic agent MUC31 in mice with CF-like lung disease. There are no relationship to disclose related to this project. As you know, airway mucus obstruction actually is a key feature of cystic fibrosis and other muco-obstructive lung disease. The airway mucus is mainly composed of two secreted mucins, the mucin 5AC and the muc5AB, and they organize into complex polymeric networks via the formation of covalent disulfide bonds, which in turn determine actually the viscoelasticity property of the mucus. It has been demonstrated, as you can see in this cartoon here on the bottom, that increased oxidation of three thiol groups of mucin monomers, actually bioreactive species, leads to abnormal cross-linking, and this actually increases the stiffness of the mucus, and is actually key mechanism underlie abnormal viscoelasticity property of mucus in our way from patients with CF. In this work, we have used the beta-INAC transgenic mouse model to test the preclinical efficacy of a new mucolytic agent. The beta-INAC transgenic mice have a constitutive lung-specific overexpression of the beta subunit of the epithelial sodium channel INAC, encoded by the gene CSNN1 beta, and this causes CF-like periciliary liquid depletion, as you can see here on the left. And on the other side, we observe a spontaneous lung disease and important features from CF, like mucus hyperconcentration and airway flapping, including also airway inflammation. This is the experimental design of the study. We decided to test the preclinical efficacy of this compound, MUC31, that is a thiol-modified carbohydrate that cleaves disulfide cross links in mucus. To evaluate the preventive MUC31 therapy on CF-like lung disease, MUC31 actually was administered to beta-NAC transgenic mice before the onset of the lung disease, so at day 0, so just after birth. And the treatment was done for 14 days. The concentration of the compound used was 1 microliter per gram of body weight, and we were treating the mice 2 times per day. During this treatment period, actually, we were monitoring the growth and the survival every day. And after 12 hours, after actually the last treatment period, mice were euthanized, and the bronchial alveolar lavage was performed to determine the inflammatory cell count, and lungs were processed for histology and morphometry to assess the mucus content in the airway. So in this slide, you can see the effect of MUC31 treatment on mortality in neonatal beta-NAC transgenic mice. So we have in light blue and dark blue, the wild-type mice, the vehicle, and the one treated with MUC31. In light green, you observe the beta-NAC transgenic mice treated with vehicle alone, and in black, we have the beta-NAC transgenic mice treated with the compound. All wild-type neonatal mice treated with MUC31 or vehicle control survived to all the treatment, so to the 14 days. And the beta-NAC transgenic mice treated with vehicle alone actually show a mortality of circa 46% that was actually rescued to circa 13% with the treatment of the compound. So what we decide actually is next to evaluate the effect of the treatment with MUC31 on inflammation, and we just then determine the total cell count in bulk. So here on top you see the total cell number in bulk. In green again, so in green we have the beta-NAC transgenic mice treated with vehicle, and the beta-NAC transgenic mice treated with compound that show actually a significant reduction of the total cell count. We had a look also to the other cell population, in particular neutrophils, macrophages, and eosinophils. And we observed no differences in neutrophils level, a reduction, but was not significant in macrophage number, and a significant reduction in eosinophil number. Here, actually, on the left part of the slide, you can see a representative picture of a differential cell count that we were using actually to evaluate the cell number and inflammatory response. Since one of the most important pathological features in the beta-NAC transgenic overexpressing mice is actually the airway mucus obstruction, we next measure the effect of preventive MUC31 treatment on mucus content in the airways. To do this, we just perform a pus staining. So here you see a representative picture of the pus staining and the quantification. And we observe actually that there was a clear trend to reduce the mucus plaques in the beta-NAC transgenic mice treated with the compound compared to the vehicle group. Additionally, we were also evaluating the levels of MUC5B in bulk by using agarose gel electrophoresis. So here you see actually a picture from the Western blot, a representative picture from Western blot, and the quantification. And then we actually were able to detect a significant reduction of MUC5B expression in beta-NAC transgenic mice treated with the compound. In conclusion, the preventive treatment of mice with CF lung disease with intrapulmonary delivery of the novel reducing agent MUC31 reduced spontaneous pulmonary mortality, as we saw in the first slide, airway inflammation, and also mucus plaque formation. This data, although preliminary, provide rationale to evaluate the therapeutic effect of MUC31 in clinical study in patients with CF and potentially actually also other muco-obstructive lung disease. Actually, I want to acknowledge my department, the Department of Pediatric Pulmonology, Immunology, and Intensive Care Medicine and Cystic Fibrosis Center Charité, the collaborators, in particular the Professor John Fay, and also all the other collaborators and also the findings. And thank you very much for your attention. And yeah, I will be welcome actually to answer any question coming.
Thank you. That was a great talk. So we do have some questions coming in. The first question is, do these mice get airway infections?
So this is, I mean, it's already published that these mice actually are more sensible to infection. This is something that in this particularly experimental setup, actually, we didn't check because we were more focused to evaluate the efficacy of the novel mucolytic agent. But yeah, this is already published, yeah.
And then as a follow-up, what is the relationship between mucus plugging, inflammation, and infection in this model?
I mean, it's already known that, okay, there are different triggers that actually induce this stiffness of the mucus and this mucus plug in the airway. And of course, one of the critical point is also accumulating of elastase. And this trigger inflammation mainly from neutrophils that so there is definitely an increased inflammation in the airway, and of course, this is make the airways more actually available for lung infection. Yeah, there are several papers actually published from our group that describe actually what is the mechanism in details to that connect the mucus accumulation and airway inflammation. That is also a common feature in CF patients.
Okay, and the next question is from JP Clancy, who asks if MUC031 has effects on CF mucus, either patient-derived sputum or on mucus clearance in CF HBEs.
Yeah, so we have also preliminary data. With the treatment actually of the MUC31 in CF mucus, so ex vivo, what we are now wanted to do is also test what is the effect of the treatment in the sputum from CF patient and maybe measure rheological property to characterize a bit better what is actually which are the properties of the mucus and how this compound can affect. We have already some data that actually comes from the main collaborator of this project, Professor Jun Fai, okay, I'm mainly focused actually on the preclinical efficacy in mice. So yeah, this is actually the main focus of my project. But yes, we have also other data in sputum from CF patients.
Okay, and then the next question is, did your compound increase MCC in the transgenic mice?
So actually, this is what we are doing now. As I said, these are very preliminary data. So we did something actually a lot more in addition to what I present. And this is actually the next point on my agenda. We will definitely check if there is an increased MCC in these transgenic mice after treatment with MUC31. It's definitely the next step we want also to check. Yeah. So thank you for the question. Yeah.
Right, and then the next question is, how did you deliver MUC031 to the mice?
So we do intranasal instillation of the compound, and the dose that we use, as I said, is 1 microliter per gram of body weight, 2 times per day. So normally we do a treatment in the morning and the afternoon, yeah, intranasal. I want also to add, if I have 2 minutes, so we want also to test the compound in other preclinical settings. So we also plan to treat the mice intratracheal, but this study was focused with intranasal instillation.
Okay, great. And then the next question is from Steve Rowe. He says, have you seen differential effects in young mice versus old mice where the amiloride ENaC inhibitor has had different effects in this model?
We have already data. What I showed today actually is the preventive effect of the compound, as I said, in newborn mice. So we just started treatment after the birth. We also have data in adult mice, in particular 6 weeks old mice. At the moment, I have to say that also the preliminary data in these different setting show the same efficacy of the compound. So I have to say that more or less the effects are overlapping. Yeah, but we need to generate more data actually to corroborate this hypothesis. Yeah.
Okay, thank you very much.
Thank you.
Annalisa. I think that's all the
Thank you.
questions we have for today. So as a closing, thank you again to the speakers. You all did a phenomenal job. Anybody who has any more questions or wants to see the data in more detail can visit the speakers posters. And I would also like to thank very graciously my co-host, Katie Heisert, who has been sending me all these questions. So I just have to read them out. So thank you everybody for speaking and for coming, and it was a great session.